Alright, welcome to Chapter 10, still talking about thermodynamics. This is Section 2A, and we're going to talk about energy conservation. So the first things we're going to do is we're going to illustrate how the first law of thermodynamics is a statement of energy conservation, and then we're going to look at calculating heat, work, and the change in internal energy by applying the first law of thermodynamics. In the next video, we'll apply the first law of thermodynamics to describe something called cyclic processes. So I want you to remember our roller coaster. We've previously discussed how when friction is present, it has to be total energy that is conserved, not just mechanical energy, but total energy. And this is because as that roller coaster goes up and it goes down, okay, some of the potential and kinetic energies are converted to heat by friction, okay, and they raise the internal energy of our system. And remember that includes the air, the tracks, the wheels, everything in our system as we define it. So the conservation of our total energy, we're now going to look at it as being called the first law of thermodynamics. So before, where we talked about conservation of energy in terms of potential energy, kinetic energy, and internal energy, now, because it's thermodynamics, we're going to look at it in terms of heat, work, and internal energy. So what would that look like? Well, mathematically, the way we express the first law of thermodynamics is just that the change in internal energy will be equal to the heat added to the system minus the work that is done by the system. Okay, so let's take a closer look at this. This conservation of energy, this first law of thermodynamics, this is what led us to our three ideal thermodynamic processes. And as we talk about this, it's important that we look at the signs of each of what these variables mean. So there's a handy table in your book, and that table is on page 343 of our text, but I do have it here on the next slide. So here, and I'm just going to write our first law up here again so we can look at this and refer to it as we discuss. So our change in internal energy is equal to the heat, okay? And notice here, if this is not negative, if it's greater than 0, we're talking about the energy added. So really that's just the same way we talked about heat before. So if it becomes negative, that means that heat has left the system. And if it's 0, there's no transfer of energy as heat. Our work now here defined, we have them being subtracted. Okay, so if our system does work, which means an example, since we're talking about gas, is if we expand our gas, so if our balloon gets bigger, okay, if it does work, it's positive. So you notice that Q minus W, if they're positive, minus positive, will either get 0 or a positive number for the change in internal energy. Okay, but if work is done on the system, so if instead our balloon gets smaller, okay, then we'll have a negative value of W, it'll be less than 0, and no work done, W equals 0. So this kind of helped me create the table that we looked at in the last video. And here's the table from your book just on. Okay. And so it lists as isovolumetric, isothermal, adiabatic, and then it talks about an isolated system. Isolated system just means that no energy is transferred as heat and no work is done on or by the system at all. Okay, so isovolumetric, we get no work done, we get W equals 0, we know the volume doesn't change. Okay, so delta U must equal Q. So energy added to the system as heat increases the system's internal energy. That's what that means. And I'm not going to go through this in detail, but I really wanted to point that out. The one thing I do want to point out here is that delta U equals negative W. Okay, so work done on the system, okay, that means W is less than 0, increases the system's internal energy, and work done by the system decreases the system's internal energy. So go ahead and take a second to review this here or in your book, and it really just summarizes what we talked about before and combines it with our first law of thermodynamics. And that is the end of our section A video for 10.2. Let me know if you have any questions.